In this class, we will look at the algebraic method to solve minimization problems. We consider the same minimization problem that we used, the same problem that we solved using the graphical method. So, the problem minimizes 7x1 plus 5x2 subject to x1 plus x2 greater than or equal to 4, 5x1 plus 2x2 greater than or equal to 10, x1 x2 greater than or equal to 0. Now, once again we will follow the same procedure where we convert the inequalities to equations and we try to solve the equations. So, as we did before, we will consider the two constraints. We will at present leave out the objective function and the non-negativity. So, the two constraints are x1 plus x2 greater than or equal to 4 and 5x1 plus 2x2 greater than or equal to 10. Now, let us look at x1 plus x2 greater than or equal to 4 and convert it to an equation, and we do it as follows. Now, this constraint x1 plus x2 greater than or equal to 4 is now written as x1 plus x2 minus x3 equal to 4. Now, x1 and x2 are greater than or equal to 0 and we want x1 plus x2 to be either equal to 4 or more than 4. So, we introduce the variable x3 such that if x1 plus x2 is more than 4, then x3 would take a positive value and then make it equal to 4. So, that x1 plus x2 minus x3 is equal to 4. If x1 plus x2 is exactly equal to 4, then x3 will take value 0. Now, x1 and x2 have to be such that they ordinarily should not be less than 4. Therefore, x3 does not take a negative value. So, x1 plus x2 greater than or equal to 4 is now rewritten as x1 plus x2 minus x3 equals to 4. So, x1 plus x2 greater than or equal to 4 is now written as x1 plus x2 minus x3 equals to 4. Now, this x3 is called a surplus variable. It is also a slack variable, but because x3 has a negative sign, it is also called a negative slack variable or it is called a surplus variable. So, when we have a greater than or equal to constraint like this, now that would result in a negative slack or a surplus variable. In a similar manner, 5x1 plus 2x2 greater than or equal to 10 is written as 5x1 plus 2x2 minus x4 equal to 10. Now, the minus x4 comes because when 5x1 plus 2x2 exceeds 10, then x4 will take a positive value to make it equal to 10. If 5x1 plus 2x4 is exactly equal to 10, then x4 will take 0. We also should have x1 x2 such that 5x1 plus 2x2 is greater than or equal to 10, 5x1 plus 2x2 is not less than 10 and therefore, x4 does not take a negative value. So, when we have a greater than or equal to constraint, we have a negative slack variable or a surplus variable introduced. x3 and x4 have been introduced, and importantly x3, x4 are greater than or equal to 0 and they will have a negative sign if we have a greater than or equal to constraint. In the earlier class, when we had a less than or equal to constraint, we introduced x3 and x4 as positive slack variables. Again x3 and x4 were greater than or equal to 0, but x3 and x4 had a plus 1 sign appearing. So, when we convert an inequality to an equation by adding a slack variable, we could add a positive slack variable if the constraint is less than or equal to type, and a negative slack if it is greater than or equal to type. But what is important is that the slack variables are defined as greater than or equal to 0 in both the cases, just as the decision variables are defined as greater than or equal to 0. So, once again we observe, like in the previous example, that with the addition of the two slack variables we now have two equations, but we have 4 variables. We also know that if we have two equations we can only solve for 2 variables. Therefore, we follow a similar manner like what we did in the previous class to try and solve this system that now has 4 variables and 2 equations. Just as in the previous example, the negative slack or surplus variables do not contribute to the objective function, and therefore they contribute a 0 to both x3 and x4. We now go on to solve this system that minimizes 7x1 plus 5x2 plus 0x3 plus 0x4 subject to x1 plus x2 minus x3 equal to 4, 5x1 plus 2x2 minus x4 equal to 10, x1, x2, x3 and x4 greater than or equal to 0. Now the linear programming problem that we have to solve is to minimize 7x1 plus 5x2 plus 0x3 plus 0x4 subject to the two constraints and non-negativity. Since we have 4 variables and 2 equations, we can only solve for 2 variables at a time, and these 2 variables from 4 given variables can be chosen in 4C2 or it can be chosen in 6 ways. So, it can be chosen in So, it can be chosen in 4C2 ways or it can be chosen in 6 ways. Now, these 6 ways of choosing the 2 variables are shown here. For example, one of them would be to solve for x3 and x4, another one could be to solve for x1 and x3 and so on. Now, when we choose the 2 variables in any one out of the 6 ways, we have the other 2 variables which we are not solving for, and these variables have to be fixed to some arbitrary value. Now, they can be actually fixed to any arbitrary value, which means they can take infinite values, but as we did before in the previous example, we fix those variables to 0. So, these variables which we are fixing at 0 or these variables which we are fixing, variables fixed to 0 are called non-basic variables, and those variables that we are solving are called basic variables. So, at a time we take 2 variables out of the 6 and solve for them by fixing the remaining 2 variables to 0. So, now let us go back and look at all the 6 possible solutions. So, first let us look at the case where we are going to solve for x3 and x4 by fixing x1 and x2 to 0. Now, when we fix x1 and x2 to 0, I am kind of deleting x1 and x2. So, we are going to solve for x3 and x4. So, we solve for minus x3 equals 4, minus x4 equals 10, which gives us a solution x3 equal to minus 4 and x4 equal to minus 10. It gives us this solution. Now, when we consider this solution where x1 equal to 0, x2 equal to 0, x3 equal to minus 4 and x4 equal to minus 10, we have this solution where x3 equal to minus 4 and x4 equal to minus 10 violates the non-negativity restriction, and therefore, this solution is infeasible. So, this solution becomes infeasible because it violates the non-negativity restriction. Now, we look at the second instance where x1 and x3 we are going to solve, and we are going to fix x2 and x4 to 0. So, we are going to if we take the second instance, we are fixing x2 and x4 to 0, and we are going to solve for x1 and x3. Since we are fixing x2 and x4 to 0, I am leaving them out. So, I am going to solve x1 equal to 4, 5x1 is equal to 10. So, 5x1 equal to 10, x1 minus x3 is equal to 4. So, 5x1 equal to 10 gives me x1 equal to 2, gives me x1 equal to 2, and when I substitute x1 equal to 2, I will get x3 equal to minus 2, so that x1 minus x3 is equal to 4. So, we have a solution x1 equal to 2, x2 equal to 0, so x2 equal to 0, x3 is equal to minus 2, and x4 is equal to 0. Now, because x3 is equal to minus 2, it violates the non-negativity restriction, and therefore, this solution also becomes infeasible. Now, we look at the third out of the 6 problems, where we are going to solve for x1 and x4, and we are going to fix x2 and x3 to 0. Since I am fixing x2 and x3 to 0, I am removing x2 and x3 from this solution. So, this gives me a system where x1 is equal to 4, this gives me a system where x1 is equal to 4 and 5x1 minus x4 is equal to 10. So, x1 is equal to 4 is shown here, that is the solution, and when I substitute 5x1 becomes 20, therefore, x4 becomes 10, so that 5x1 minus x4 is equal to 10. So, I get a solution x1 equal to 4, x4 equal to 10. So, x1 equal to 4, x2 equal to 0, x3 equal to 0, x4 equal to 10 satisfies the non-negativity restriction, and therefore, it is feasible. It is a basic solution because I am solving for 2 variables. I am solving for 2 variables because I have 2 equations. So, this solution is both basic and feasible, therefore, it is basic feasible. Now, I compute the value of the objective function for x1 equal to 4, x4 equal to 10. So, 7 into 4 plus 5 into 0 gives z equal to 28. The value of the objective function is 28. Now, we move on to the fourth out of the 6 solutions. Now, in this solution, I am going to solve for x2 and x3, and I am going to fix x1 and x4 to 0. So, I am going to fix x1 and x4 to 0. So, this goes, this goes, this also goes. So, the second equation becomes 2x2 equal to 10, from which I get x2 equal to 5, from which x2 is equal to 5, and if I substitute x2 as 5, I get 5 minus x3 is equal to 4, therefore, x3 is equal to 1. So, I have a solution x1 equal to 0, x2 equal to 5, x3 equal to 1, x4 equal to 0, and this solution is feasible because it satisfies the non-negativity restriction. It also satisfies the two equations. It is also a basic because I am solving for two variables x2 and x3 and I have two equations. So, I have a basic feasible solution, therefore, I try to find out the objective function value. So, the objective function value would be 7 into 0 plus 5 into 5, which gives me z equal to 25. Now, I move on to the fifth of the 6 problems, where I am going to fix x1 and x3 to 0 and I am going to solve for x2 and x4. So, I fix x1 and x3 to 0. So, x1 and x3 to 0. So, the first equation gives me x2 equal to 4. First equation gives me x2 equal to 4, which is shown here, and when I substitute x2 equal to 4, 8 minus x4 is equal to 10, which gives me x4 is equal to minus 2. Now, when x4 is equal to minus 2, it violates the non-negativity restriction and therefore, this solution is not feasible. So, it becomes infeasible and this is written as infeasible. Now, we go to the last of the 6 situations. Now, the last one I am going to solve for x1 and x2, I am going to fix x3 and x4 to 0. So, I am going to fix x3 and x4 to 0. So, this goes, this also goes. I have to solve for x1 plus x2 equal to 4, 5x1 plus 2x2 equal to 10, and I multiply the first equation by 2 to get 2x1 plus 2x2 is equal to 8. Subtracting, I will get 3x1 is equal to 2, x1 is equal to 2 by 3. I will get x1 is equal to 2 by 3, which is shown here. Now, when I substitute x1 is equal to 2 by 3 in x1 plus x2 equal to 4, I will get x2 is equal to 10 by 3. So, that x1 plus x2 is 12 by 3, which is 4. Now, this satisfies the non-negativity restriction and therefore, it is feasible. It is also a basic because I am solving for two variables since I have two equations. So, it is a basic feasible solution. Now, I calculate the value of the objective function for this. So, 7x1 plus 5x2 will become 7 into 2 by 3, 14 by 3, plus 5 into 10 by 3, 50 by 3, which will give me 64 by 3, which is equal to 21.33. Now, out of the 3 solutions which are basic feasible, the one that has the lowest value, minimizing the objective function, the one that has the lowest value is optimum, it is the best solution. So, the solution 2 by 3 comma 10 by 3 is optimum to the minimization linear programming problem. In the next class, we will see some more aspects of the algebraic method and we will try to relate the algebraic method to the graphical method.